So this is the AP Physics C 2010 number 1 presentation. So students are able to conduct an experiment to investigate the relationship between the terminal speed of a stack of falling paper coffee filters and its mass. The procedure involves stacking a number of coffee filters like the one shown in the figure above and dropping the stack from rest. The students change the number of filters in the stack to vary the mass m, while keeping the shape of the stack the same. As the stack of coffee filters falls, there is a resistance force, drag force, acting on the filters. The students suspect that the drag force, Fd, is proportional to the square of the speed, Fd equals Cv squared, where C is constant. Using this relationship, derive an expression relating to the terminal speed, Vt, to the mass m, and a table of data. So we would do an F equals ma equation, with mg going down, because down would be positive in this example, minus the drag force, Cv squared. And because we know that it has reached terminal velocity, we know that the drag force is going to be equal to the mg to cancel it out. So we can set it equal to 0. So when we do that, we get v squared equals g over c times m. The next question asks us to make a graph. Assuming the functional relationship for the drag force above, use the grid below to plot a linear function, so a straight line, to verify the relationship. Use the empty boxes in the data table as appropriate to calculate any calculated values you are graphing. So in our equation, we would have m on the x-axis and v squared on the y-axis. So we would calculate that here with vt squared in the bottom row, and you would get these values. And when plotted, you would have these black dots, which would be your vt squared values. And then you would make a line of best fit, as seen here, which is this blue line. Use your graph to calculate C. So first, we would choose 2 points. I chose 2.8, 0.6, and 0, 0. And you would calculate the slope, which I found to be 214.285. And based on our equation, we know the slope is going to be equal to g over c. So when we cross multiply, we get g over the slope is equal to c. So c would be 0.047. Now, a particular stack of filters with mass m is dropped from rest and reaches a speed very close to terminal speed by the time it has fallen a vertical distance y. Sketch an appropriate graph of speed versus time from the filters released from t, time equals t, that the filters have fallen the distance y. Indicate time t and terminal speed vt on the graph. So first of all, vt would be a line that the graph approaches, which is its terminal speed. And if we look at the force, we see that v squared is equal to, or we see that the force over here is equal to cv squared. So as v increases, there'll be a greater force counteracting the gravity, so the acceleration would decrease. So we should have a concave down graph that approaches our asymptote of vt, and t would be the time that it reaches that line of terminal speed. Suppose you had a graph like the one sketched in CI that had a numerical scale on each axis. How could you use the graph to approximate the distance y? So you would basically want to take the area under the graph, because the distance is the area under the graph. So you would take the integral from 0 to t being the time it takes to get to, or the total time that you want to calculate, and vt being the function. And that would give you y. Finally, determine an expression for the approximate amount of mechanical energy dissipated due to air resistance during the time the stack falls at distance y. Express your answer in terms of y, m, and fundamental constants. So first of all, change in mechanical energy is going to be gravitational potential energy and kinetic potential energy in this case. So the change in kinetic is going to be equal to 1/2 mv squared, and the change in gravity is going to be equal to m negative mgy. So since it starts at rest, it's gonna at least keep the amount of energy that is that its terminal speed um as the gravitational energy goes to kinetic energy. However, it's going to be losing mgy because once it reaches terminal velocity, it's no longer gaining more kinetic energy, and that gravitational potential energy is just disappearing. So you would just subtract that, and then that's all. So you would have, after factoring out the m, you would have m times negative gy plus 1/2 v squared equals the change in total energy.